It's a pleasure to have Xiaoxun here give us the BIDMaP Emergent Scholar talk. And Xiaoxun is a PhD student from Professor Stephen Louie's group in the Department of Physics at UC Berkeley and LBNL. So he is one of the major developer of DeepH and DeepH E3 method for deep learning in electronic structure. And before joining UC Berkeley as a graduate student, and Xiaoxun worked with Professor Yong Xu and Professor Wenhui Duan at Tsinghua University as an undergrad student. And but meanwhile, he holds a bachelor from Peking. So let's welcome Xiaoxun to the talk.
Yes, thank you. Okay, thank you for the introduction. So today I'm very happy to be here to present my work, which is a collaborative work between Tsinghua University and UC Berkeley. So I'm Xiaoxun. I'm from Professor Stephen Louie's group at the physics department. So today I'm gonna talk about my work about accelerating electronic structure calculations using deep neural networks. So let me first give an introduction about my work. So when we talk about different levels of methods in the quantum chemistry or ab initio calculations, most of us can think about the Jacob's ladder, but we have to also keep in mind that whenever we go higher in the Jacob's ladder, the cost we pay is that we will we will need to put in much more computational resources. So this is the well-known accuracy efficiency dilemma of the first principles calculations. So here I have summarized some representative calculation methods. So on the left hand, we have the most efficient one, but the least accurate ones, like semi-empirical methods, like tight binding models. And in between, we have the density functional theory and the Hartree-Fock theory. And on the most accurate side, but the least efficient side, we have GW-BSC methods, and also the multi-reference methods and quantum Monte Carlo calculations. So the thing I'm going to talk about here is that we will seek help from artificial intelligence and big data in order to break this accuracy efficiency dilemma of the first principles calculations. So in the traditional paradigm of scientific research, whenever we have a physical system, we want to predict the properties of the physical system, we have to rely on the human intuition and the trial and error in order to find a working model and algorithms to help us predict the properties of physical systems. Now, with the help of artificial intelligence and big data, which will be unified under the framework of deep learning ab initio calculation, which I will present in my talk, we can avoid this human intuition and trial and error, and let the artificial intelligence discover the physical laws that are hidden behind the big data, and let this intelligence tell us the properties of the materials. And when we have accumulated enough information and experience on the properties of the physical systems, we can further utilize our deep learning ab initio calculation framework to help us inversely design the material given the properties that we need, and then we can synthesize the materials to put into the for further research or applications. So what is the deep learning ab initio calculation? So the thing I want to present here is that the deep learning ab initio calculation is the development of ab initio calculation methods with deep learning techniques that have two defining characteristics. The first defining characteristic is that these deep learning methods are much more efficient than traditional methods, of course. And meanwhile, we also want our deep learning methods to maintain the same level of accuracy as traditional methods. One of the most successful example is the deep learning potential method, which we use the neural network or machine learning methods to learn the mapping between the input atomic species and coordinates to the output energies and forces. So when we have the total energy and forces of structures, we can do a lot of things. So for example, these deep potential method has already enabled efficient molecular dynamic simulations for systems up to 100 million atoms. So when we can do molecular dynamics at such a large scale, we can do unprecedented applications of like drug design and chemical reaction simulations and so on. And we can, of course, we can also relax the structure to find the optimal atomic configurations. So this is the first step I'm describing about deep learning and using deep learning and big data to predict the properties from the physical system. And perhaps I don't need to explain to everyone here why deep learning works so well with big data, and deep learning automatically wants to combine with big data. And people building from the deep learning potential methods, people are trying to build foundation models like these universal deep learning potentials that are trained on a diverse data set of different kinds of materials, and then they can be used to predict the properties, predict the total energy and forces of systems in the diverse chemical environments. And these are the so I'm only listing a few of the most well-known models that are universal deep learning potentials. So once we have these large models of total energy and forces, we can do inverse design, which is the final step described in this diagram. So the large deep potential models can enable us to discover materials to discover stable materials at an unprecedented scale. So the GNOME project is the most well-known project of this kind. It has so using deep learning potentials, so using universal deep learning potentials, the GNOME project has discovered 2 million stable structures of this is of the same order as the number of structures in the materials project. And this Open Materials 2024 is also a project led by Meta that's building a big data of like hundreds of millions of structures to train our universal deep learning potential models. So as I have described in my last slide, the deep potential methods aims at learning the mapping between the input atomic structure to the total energy and forces. And these are majorly atomic structure simulations because we are only care about the total energy and forces of each atoms. But what about going one step further and consider the electronic structure simulations? So the electronic structure is it's like a very broad term, and it majorly refers to the quantum state of electrons of atoms, molecules, and materials. So let me give a very brief introduction of density functional theory here. So so in the density functional theory is mostly you can understand it as mean field theory, which maps this many-body Hamiltonian to a single body Hamiltonian using mean field approximations. So the mean field Hamiltonian is so the mean field Hamiltonian here is a function of electronic density, and so here we have the first term is the kinetic energy term, the second term is the interaction between electrons and ions, and the third term is the Hartree potential, and the final term is the exchange correlation potential. So we can see that the Hamiltonian, the mean field Hamiltonian here is actually a functional of electronic density. So that's why we call this theory a density functional theory. And the electron density comes from the wave functions. So when we diagonalize the Hamiltonian to get the wave functions, we can use our wave functions to build the density, and then we will substitute the density back into this formula for the Hamiltonian, and then we do self-consistent iterations. So this is the typical workflow of a density functional theory calculation. We start from atomic positions and coordinates, atomic positions and species, and then we guess the first density. Then with that we build our Hamiltonian based on our mean field approximation. We diagonalize the wave function, we get another density, and then we do self-consistent iterations until the final Hamiltonian reaches convergence. And then from this final Hamiltonian of density functional theory, we can get our desired electronic structure properties of materials or structures. So so in our work of deep learning Hamiltonian, what we are thinking about is exactly like a deep potential method. We start from we start from the atomic structures of the material, but we use our neural network to predict the density functional theory Hamiltonian instead of the total energy. So in conventional density functional theory, we have to go through all of these steps until we reach the final electronic structure properties. But here, using our deep learning method, we skip all of these steps. We start from the atomic positions and the species, and then use deep learning to directly give us the final converged Hamiltonian of the structure. And then from this structure, we can give us basically all DFT-based physical properties of the materials. So in my talk today, I will discuss two topics. So the first topic is the DeepH E3 method, which is a neural network designed with physical insights. And then I will discuss the applications and extensions of the DeepH E3 method. So let me briefly introduce the method workflow so you can have a better understanding of what we are actually doing. So in our DeepH framework, we are training our neural network directly on DFT calculated Hamiltonians. So suppose we have a data set that has many structures in it, and then of course, we can use our neural network to predict the Hamiltonians of these structures. And then we can also use DFT calculations to calculate the Hamiltonians of these structures. And in our training process, we try to minimize the error between the predicted Hamiltonian and the DFT calculated Hamiltonian. So this is pretty straightforward, right? And the result is quite significant. So we can achieve orders of magnitude acceleration compared to conventional DFT methods. So one of the most successful example of our framework is the magic angle twisted bilayer graphene, which has 11,000 atoms. So this, in case you don't know, this magic angle twisted bilayer graphene is like, graphene is like a single sheet of carbon atoms. We place one sheet of carbon atom on top of another, and then we slightly twist one of the layer with respect to the other, and then we create a very large supercell. And we have these Mori patterns and all of these Mori physics, which has been quite a heated research topic these years, and because of the discovery of superconductivity and a series of correlated electronic states. So because this magic angle twisted bilayer graphene has a very large structure, it is very difficult to be computed using conventional DFT methods. And if we do brute force DFT, we will need more than 3,000 CPUs and do computation for 1 month. But with our DeepH E3 method, we only need to train our model on a single graphics card in a personal computer. The training process only takes 2 days, and we can reach an error. So the predicted Hamiltonian only has an error that's on the order of millieV compared to brute force DFT calculations. So let me introduce to you how we can achieve such a great success. So the most important thing, according to our experience, is that we are designing our neural network with physical insights. So the first physical insights I'm going to discuss today is about the locality of Hamiltonian. So the locality of Hamiltonian, so first I would like to say that we are using the Hamiltonian under atomic orbital basis. So the atomic orbital bases are local, so that we can use these local atomic orbital bases to take advantage of the locality of Hamiltonian. So the locality of Hamiltonian basically means that the Hamiltonian matrix element between 2 atomic orbitals will go to 0 when the 2 orbitals are far apart from each other. This basically means that the electron cannot hop infinitely long distances in the material. So the direct consequence of this locality means that the Hamiltonian is a sparse matrix if we express the Hamiltonian under a basis set of atomic orbitals. And another thing is about the nearsightedness of electronic structure. So the nearsightedness of electronic structure tells us the Hamiltonian is only determined by a nearby atomic environment. So what this means is that if we are only interested in a Hamiltonian matrix element, let's say at this green point, and then we slightly perturb an atom that's very far away out of certain cutoff radius, like right here, we perturb an atom right here, and we would imagine that the influence of this perturbation of atom positions is negligible on the Hamiltonian at this green point. So this is basically the nearsightedness of electronic structure. So our first physical insight here to the neural network is that the neural network must only take the local atomic structure to determine the local Hamiltonian. There are several direct benefits of this physical insight. So the first is linear scaling of our method, and which is very obvious because we are only using local information to predict the Hamiltonian. And then our method can also learn from small structures and predict the much larger ones. In fact, the structures in our data set, the structures in our data set only needs to be larger than the sphere with a certain cutoff radius RC.
So you still need to diagonalize the Hamiltonian boundary.
Yes.
So it's not linear. In total, it's not linear scaling.
Yeah, but so the Hamiltonian is a sparse matrix, and in most application scenario, we only need the information around the Fermi surface, so we can selectively diagonalize a small spectrum that's close to the Fermi surface, and then if we limit ourselves to a few bands that are closest to the Fermi level, then this method is still linear scaling.
Okay.
Yeah, but if you have some advanced applications of this method, then yeah, sure, the diagonalization will become a bottleneck. Okay, so let me briefly introduce the neural network architecture we are using. So we are using the message processing neural network on crystal graphs. So what is a crystal graph? A crystal graph basically means that if we have a material and we treat each atom as a node in the graph data structure, and then we connect edges between the nodes where there's non-zero hopping, which is the Hamiltonian matrix element between two atoms. And then we assign higher dimensional vectors to edges and nodes, and following the conventions in the machine learning community, these higher dimensional vectors are called the feature vectors of the nodes and the edges. And the message processing process is basically the features of nodes and the edges are updated using other features in its vicinity. So, for example, if we want to update the node feature of this red node, we only take the information in its vicinity, that's these edges and the nodes that are connected to this node, to this central node. So this is a very, very simplified schematic illustration of the message passing process. So once we have our input to the neural network is basically the atomic species and atomic positions. So the atomic numbers are we can do just the embedding, and this will become the initial starting point of our node feature, and then the relative distance of two nodes, the relative positions of two atoms basically become the starting point of our edge feature. And then we do several message processing process and iteratively update our nodes and edges. And then in the final layer of the message processing neural network, we take the output edge feature as our hopping between two atoms, between like atomic orbitals centered on two atoms.
Is the Gilmer paper that you cite related to DeepH or just general?
This is just general message processing. Yeah. And okay, so the next physical insight I'm going to discuss here is about the equivariance, or in a physics community, it's more termed as covariance. These two terms are basically the same thing. They have slight differences, but basically here you can treat them as the same thing. So the thing we want to discuss here is that there is a fundamental law which says all physics must be covariant under global translations and rotations of the structure. So as a quantum operator, the Hamiltonian we want to predict using our neural network should also obey a certain quantum mechanical transformation rule, which is display like this. And so our next insight of our neural network is that our neural network must respect fundamental symmetries of the physical laws. That is to say, if we give the neural network a rotated structure, the neural network must also output a rotated Hamiltonian as well. And there are also, of course, different possible realizations of this constraint. So the most brute force method is data augmentation. So for every structure in this training set, we can randomly rotate it several times, and then let the neural network learn the covariant role by itself. But a more clever way is to make everything in a network covariant, and we take advantage of the equivariant neural networks, which in these equivariant neural networks, all the equivariant features of this equivariant neural network are built from vector spaces of irreducible representations of the SO3 group. So the SO3 group is basically the rotation group, and the rotation group in the three-dimensional space. And the irreducible representations are like fundamental objects that transform covariantly under the SO3 rotations. So using this method, we can achieve covariance in our neural network. So let me explain a little bit in more detail about how we realize our equivariance. So as I said in my last slide, so every vector in the equivariant neural network will carry an angular momentum. These are representations of the SO3 group. And so the atomic numbers, of course, they are invariant under the rotations. So they have angular momentum, quantum number 0. And interatomic distances, they are also invariant, so they also have angular momentum 0. But the atomic relative positions, if you expand the relative positions with spherical harmonics, then we can have non-trivial representations under the SO3 group, which correspond to angular momentum 1, 2, and 3, and so on. So we pass all these equivariant features into our neural network, and inside the neural network, all features are also equivariant, and the final output Hamiltonian is also equivariant, which is the Hamiltonian has a representation of the tensor product representation, which is basically the angular momentum of the atomic orbital on the one side, and a tensor product, the angular momentum of the atomic orbital on the other side. So the benefits of equivariant architecture. Of course, the most important benefit of the architecture is that it satisfies the fundamental physical constraints of the physical system. But I will briefly summarize a few other important benefits of the equivariant architecture. So the equivariant architecture gives us a more natural way to include directional information. So in principle, of course, we can reconstruct the whole crystal only using these distances between any two atoms. But of course, we want to give the machine more information to help it give a better prediction. So we want to also give the relative position information, which are vectors that can be rotated on the rotations. So if we don't use the equivariant architecture, then we have to design very complex features, including some angles and three-body angles and so on, and also all of these descriptors. But in these equivariant neural network, we can directly use spherical harmonics to expand the relative positions, and this provides a very natural way to include directional information into the neural network. And because of this equivariant constraint, we can imagine that the neural network can achieve the same prediction with less parameters, because you can imagine different parameters can be related by this constraint of equivariance. So of course, this can give us more efficient neural networks and also prevents overfitting. And this neural network, this equivariant architecture also allows much higher data efficiency. So according to our tests and also tests of previous works, we have found generally this equivariant architecture requires much less data to train, and in order to achieve the same level of accuracy. All right, so there is a further improvement of this equivariant architecture. So some previous works can reduce the SO3 problem to an SO2 problem. So the basic idea is like follows. So for every bond in the structure, we can define a local coordinate system. We rotate the global coordinate system to a local coordinate system that's specific to this bond. We choose this local coordinate system such that the z direction of the local coordinate is pointing in the direction of the bond. So instead of a rotation degree of freedom in a three-dimensional space, we reduce our problem to a degree of freedom which is rotation in the xy plane, and because we keep the z-axis fixed. So we reduce the problem from SO3 to SO2. And let me give you a very brief sense of how much computational effort we are reducing. So the representation of SO3 group is very difficult. It has all of these Wigner matrices, and the Wigner matrices has these very complicated formula. But the representation of SO2 is very simple. It's just the cosine and sine of the rotation angles. So by doing this, we can greatly simplify our neural network architecture, and also allows our neural network to use more parameters and fit more complex data sets.
We have found a way in the direction.
So the local coordinate is for each bond. We define a separate local coordinate system for each bond for all of the bonds.
Yeah, it's just for the message pass.
Sure. Okay.
So each message passing happens from a bond.
I mean,
Yeah.
in this direction, the wave is not taken into account, that in that direction, it won't either.
Yeah, it's a unique transformation for each message, right?
Okay, sure.
My understanding is you rotate the features on each node uniquely depending on the message we pass.
Yes. When we do message passing on this bond, then when we do everything in this specific local coordinate system.
Yeah, so there's extra computational effort to rotate things into that plane, but then you avoid,
Yeah, we can pre-compute this rotation like only once because we have the structure.
Yeah.
Okay, so now I will go to the applications of and extensions of the DeepH method. So let me go back to the magic angle twisted bilayer graphene example, which I have very briefly talked about in the beginning of my talk. So this magic angle twisted bilayer graphene has 11,000 atoms, and here we can see that so these blue dots are the brute force computed DFT band structure, and then these red lines are the DFT band structure predicted by our neural network. So we can see that the error of our method is only on the scale of milli-electron volts, which is very surprising to us, and then to us at first, but when we carefully examine what is happening inside the neural network, we can get a better understanding of why our neural network can achieve such a high accuracy. So if we look closely at the twisted structure, so at first sight, the twisted structure looks very complicated. But if we look at the twisted structure more closely, look at it locally, it is actually similar to the non-twisted structures. So at these parts, they are more similar to the non-twisted structures, which are directly on top of the other. One layer is directly on top of the other. But if we look at these parts, they are much similar to the structures which are shifted by a Hubbard unit cell. So because of this locality, because of this local similarity between non-twisted structures and twisted structures, we can actually only use our non-twisted structures as our training set. So our training set only contains 300 bilayer graphene non-twisted supercells with different interlayer stacking and also random perturbations of atomic positions. We also need to introduce random perturbations of atomic positions in our training set because in a large twisted supercell, there will be corrugations or relaxation effects, and we have to take into account these effects. So this is basically our method can work so well on the magic angle twisted bilayer graphene, and a very straightforward generalization of our method is to study the magnetic superstructures. So in the presence of magnetism, we also need to input to the neural network these magnetic moments on each atoms. So our input to the neural network is now the atomic structure plus the magnetic moments, and then we can predict the density functional theory Hamiltonian. Our application example is the magnetic skyrmion in the twisted bilayer CRI3 system. So this magnetic skyrmion is predicted in this. It's recently theoretically predicted in the CRI3 system. It is a vortex-like magnetic configuration, which is this very complicated magnetic configuration arises from the stacking dependent interlayer magnetic coupling between the different layers of CRI3 systems. So this is a illustration of the crystal structure we are interested in. So we train our neural network on the bilayer CRI3 at 60 degree. At 60 degree is basically that we don't need to create a supercell for the structure, but in our we create a supercell in our training structure, but in principle, this 60-degree twisted structure doesn't have this Mori pattern. But so it's actually much easier to calculate at DFT level. So in our training set, we use supercells of bilayer CRI3 at 60-degree twist, and then we generalize to our neural network to a superstructure of CRI3, which has 4,000 atoms. And this is our theoretical predictions. So if we ignore this vortex structure in the Mori structure of the twisted CRI3, we get a ferromagnetic coupling, and then we will have a DFT band structure that looks like this. But if we make the twisted crystal to be a magnetic skyrmion structure, then all of these bands that will simply disappear into in the DFT band structure. So this has not been experimentally confirmed yet, but this is definitely demonstrate the effectiveness of our method, and then it will opens up future experimental and theoretical investigations. And another generalization of our method is the deep learning electron phonon coupling. So in a density functional theory, this electron phonon coupling is usually studied with the DFPT, the density functional perturbation theory. So I will very briefly introduce phonons. So the phonons are nothing but collective movements of ions in the crystal. So sound wave is a very basic thing, as a very basic example of phonons. And the coupling between electrons and phonons in the solid state structure gives rise to many important physical phenomena. And one of the most interesting thing is the BCS superconductivity. It arises from electron phonon coupling, right? So in the theory of electron phonon coupling, the most central physical quantity to be studied is the derivative of the Hamiltonian with respect to the atomic position. So as I have said, the phonons are movements of ions which correspond to the change of the atomic positions, and the coupling between electrons and phonons of course, they are captured by this derivative of the electronic Hamiltonian with respect to the phonon movements of ions in the crystal. So this is the central quantity we want to compute, and so just like in the deep potential method, when we use a backpropagation to get the forces from the total energy, we can also use the backpropagation to get the derivative of the Hamiltonian with respect to atomic positions. Once we have already the forward mapping from the atomic positions to the electronic Hamiltonian. So we also follow our workflow of training on small structures and predict on larger ones. So we can train our neural network on a perturbed single sheet of graphene, and then we can generalize our network to predict on a carbon nanotube. So this is the comparison between the DFT calculated and the neural network predicted Ely-Ashburg spectral function. So Ely-Ashburg spectral function is the central quantity that's related to the superconductivity critical temperature. We can see that the predicted spectral function almost lies exactly on top of the DFT calculated ones. Okay, so we can further consider a general model for carbon. So previously I have demonstrated a specific model for carbon, which is a specific model for twisted bilayer graphene, which is only applicable to the bilayer graphene system. But here I will consider a more general model for carbon and see what happens. We will train our neural network on a data set of 426 different carbon allotropes. So this data set contains many weird looking structures, but after we train our neural network still gives a very good band structure on the magic angle twisted bilayer graphene. So we can see these red lines are the band structure predicted by the general model, and these blue dots are the band structures predicted by our specific model, which is only trained on the bilayer graphene data sets. So we can see that error is actually very small, and we can see our neural network can learn much deeper physics if we only provided a general model instead of a specifically designed. If we provide a neural network with a general data set instead of a specific designed data set with human intuitions. This is very surprising to us. And also, we can also consider twisted materials with data phase. So because of all these research that has gone into the twisted materials since the discovery of the twisted bilayer graphene, people have studied a lot on the correlated phases and all of these stuff on the twisted 2D materials. So in our recent work, we constructed a database for twisted materials. So as I have discussed before, we already have a workflow for generalizing our neural network from non-twisted structures to twisted structures. But previously we only applied it to the bilayer graphene. Now we apply this workflow to 124 different materials, which consist of twisted material database. All of these materials can include very different physics, like spin orbit coupling. There are non-magnetic materials and also magnetic materials. There are many different different compound structures of the there are many different compounds in the data set, and we have also considered heterostructures, which are one kind of material in one layer and a different kind of material in the other layer. So for almost all of these materials in the twisted materials database, the errors of the Hamiltonian are below 1 milli-electron-volt, which is very good since all of the physics happen on the energy scale of EV in condensed matter physics. And we only need one model for each of the material. We only need one model for different twist angles because once we train our model, we can predict the Hamiltonian on all twist angles instead of doing computation on all different twist angles. All right, and so inspired by our success in this first attempt in the general model, we're just using PBE functions. Yeah, GGA. Right, and so inspired by our success of this general model, we are building a more ambitious project, which is a universal materials model. So we already know from the deep learning potential model that building large models can give us new physics and give us open up new research directions. And when you have these universal models, but actually all of these universal machine learning potentials only predicts the total energy and forces of the materials. But now we are more ambitious, and we want to build a universal model that achieves general purpose property prediction for a wide range of material systems. So, and our statement here is that the Hamiltonian should be the desired target quantity for universal materials models, because first, the Hamiltonian can give us all DFT-based physical quantities, and once that we have a Hamiltonian, we can achieve a general purpose material property prediction. And also, the nearsightedness and symmetries of the Hamiltonians, as I have discussed before, these all guarantees the model transferability, which allows us to build our model on a wide range of different material systems. So we can just imagine what will the universal material models bring us. So one of the problems in the materials research is that the chemical compound space is extremely large, and because of the computational resource we only have today, even if we have increasing computational resources these years, as humans have only explored a very small, very tiny amount of the a very tiny portion of the chemical compound space. So once we have the universal materials models, we can achieve a very efficient and widely applicable property prediction and expand our study of chemical compound space to a much larger order of magnitude. And in the deep learning method applications, so nowadays the application of deep learning method is still not easy for beginners, because deep learning models nowadays are most of them are very sensitive to the trade-off training sets. As I have discussed before, we need to design a specific training sets in order to predict our physics in the twisted bilayer graphene. But now, once we have a universal material model, and we would reasonably expect that the model will gain intelligence upon seeing larger data sets, we will get rid of the problem of human intuition designing sensitive data sets that will affect the final results of our prediction. So this is the first attempt of our universal materials model. We are training our model on 10,000 compounds with elements spanning the first 4 rows of the periodic table. And we can see from here that our model actually gives excellent predicted band structure and also the electronic susceptibility. So this rank at 20% means that the error of this material is within the lowest 20%. So all of these materials are not seen in the training set; they are all in the test set. So this 20% means this MAE, that the error is like within the 20% of the test set. And this material on the right means that the error of the predicted Hamiltonian on this material is at the 80% of the test set. So even you can see this is like among the worst of the predicted band structures. It still looks very good, and we can so basically from our naked eye, we can see very small differences from the DFT band structure and the deep learning predicted band structure. And we can see all of these materials are very complex. There are different, many different kinds of elements, and also the crystal structure looks very complicated. But still, our model can handle the physics underlying these materials. And yeah, so further generalization of our method is neural network density functional theory. So we all know that the density functional theory also has another aspect, which is minimizing the total energy computed by the density functional. So we can make use of this. Make use of this principle of minimizing total energy in our training of the neural network. So once we have an auto-differentiable DFT, which gives our total energy given. Okay, so once we have our total energy given by the auto-differentiable DFT, which comes from this neural network predicted Hamiltonian, we can do a backpropagation, and during the process of minimizing total energy, we can also optimize our neural network parameters. That is basically treating our computed total energy as a loss function of our neural network, and then we will get rid of all of these DFT calculations. So this is what we call combining DFT algorithms and neural networks towards physics-informed unsupervised learning. And so there are many benefits of this workflow. So the most straightforward is that we don't need to invoke traditional DFT anymore. And there is also, once we have this auto-differentiable DFT, we can also very easily assess our errors. So previously, when we are unsure of how our neural network is performing on one certain material, we have to do a DFT calculation and benchmark our calculation. But now we don't need to do DFT anymore. We can directly compute the total energy, and then we directly have the estimated error of our neural network. And according to our test, this method also allows higher accuracy than directly trained models. So first, our test on these material systems show that the unsupervised learning, it indeed gives very good band structure compared to DFT calculations. And then for this sodium structure, we can see that the unsupervised learning indeed gives us a lower error compared to supervised learning. So and on this water molecule system, it's on the same level, but for the sodium structure, the error of the unsupervised learning is indeed lower. So this means that unsupervised learning is actually giving the neural network more information, maybe some deeper information to learn, and then it will help the neural network get a better prediction results. All right, and since we are out of time, we can just skip these two slides, and then so let's just have a brief summary of our method. So the first important take-home message is that there are two aspects of physical insights that are put into the design of our neural network, which are locality and symmetry. And the key capability of the DeepH E3 method is that this method can learn from small structures and very efficiently predict on much larger ones, and the errors are on the sub-meV error level. And because of all of these extensions and applications of this deep learning Hamiltonian method, we would like to say that it is very highly possible that in the future, electronic structure calculations will be replaced, and most of them will be based on deep learning methods. And this is my, I would like to thank my supervisors and collaborators, Professor Yong Xu, Professor Wenhui Duan, and Professor Stephen G. Louie. And thank you all for your attention, and I'm happy to take questions. Yeah.
When you're doing the unsupervised learning, do you like pre-train the model, or like what's regulating it from just making the Hamiltonian infinitely negative?
We can do both. So so if the DFT calculation for the data set is cheap, of course we can pre-train the model and then do a unsupervised learning. And then if we don't want to do DFT calculations on different structures, so for example, we already have a pre-trained model on a, and then we have like some complicated materials we want to predict the Hamiltonian, but we also don't want to do DFT calculation. We can train our model using this unsupervised learning. And in this figure, we are not using any pre-training. We are just training the neural network from the like randomly initialized parameters, and then do this unsupervised learning.
What's stopping it from just giving infinite negative energy?
You mean
why wouldn't it just predict the Hamiltonian to be infinitely negative? What am I missing? We can talk after this is
Okay. Oh, you mean there is an energy reference of the like a reference point of the total energy, and it can be infinitely negative?
Yeah. Because you're minimizing the energy, right?
Yes. So there is actually a clever way for us to get rid of this. So we can actually define a loss function that is we can define a loss function that forgets about this constant reference point of the energy, and then we can minimize the network parameters. We minimize the energy by adjusting the network parameters.
So it's just basically like the, okay, so you
Yeah.
like a traceless Hamiltonian.
Yeah, like getting rid of the trace of the Hamiltonian. Yes.
So okay, that's probably why. That's interesting that works. It's really cool.
Thank you.
Yeah, I actually had like a similar question to that of like, I guess how are the without any sort of pre-training or anything, like how are the initial predictions like even somewhat reasonable?
They are not reasonable actually. If we just randomly initialize the network parameters, it will give random numbers. But somehow this unsupervised learning, like it can guide the Hamiltonian, it can guide the neural network parameters to update, and then it will get a better physically make sense answer.
And it updates. You get. Well, because like at least from my like how I understand like the variational principle, like it works because you have some like physics built into the equations.
Yes.
You have that built into the picture here that is strange. I might just be misunderstanding.
Yeah, we already have some physics built into the architecture. Yes, but we only have like these like very general constraints like the symmetry and the locality and stuff, but we don't have any information about the specific structure in the training set. But still, somehow this unsupervised learning process can still find its way. Yeah. Regularization. You mean what kind of? Yeah.
You can minus the base.
We don't need that kind of regularization because our neural network are they're actually not small. They're actually not very large. Like if you're concerned about overfitting, then this is mostly not an issue in our cases. Yeah, because so you can imagine that so for example, if we are interested in a deep learning potential problem, so for each structure you only have one total energy as the target, but now for each structure of each structure in our training set, we have like thousands or like millions of Hamiltonian matrix elements. Yeah.
It also prevents numbers.
Yeah,
Yeah, like what is your reference for the Hamiltonian error? It's the PBE Hamiltonian.
yes.
Okay, there's no way you're gonna recover the PBE Hamiltonian without putting PBE in the data somewhere, right? For unsupervised.
Oh, it's encoded in this auto-differentiable DFT.
I have to just read the paper, but like it's not obvious to me that if you don't put PBE in there somewhere, you're not gonna you're gonna recover some other Hamiltonian of the PBE Hamiltonian, right? Like there's nothing special about the PBE Hamiltonian.
Yeah, so it's like when we predict the Hamiltonian, we diagonalize for the wave functions and we get the density, right? When we have the density, we have to put in the PBE functional and then we get the total energy.
Oh,
yeah. So all of these are encoded in this DFT auto-differentiable DFT process.
Okay, so PBE is in there somewhere.
Yes, yes.
I'm sure if I read the paper, it would make sense. It's just
yeah.
I mean the fundamental question though is I mean obviously Ed, like does this work for non-local functionals, right? Like exchange.
Yes, we have tried hybrid functionals, PBE0. This works very well. I just don't have the time to explain it in detail.
Okay. Yeah. I mean, how does like the exchange is non-local, right? So how does it? I mean, there are circumstances where I could come up with like separated atoms that have a very non-local Hamiltonian element that it seems like the model couldn't capture. I mean, I'm sure you get this question all the time, but like also if you have like an ion somewhere in your your molecule, right? Like that's gonna affect the Hamiltonian, right?
Yeah, so like even okay, so this is like a quite complicated question. So um the exchange, so the exact exchange is non-local, yes, but if we sum over, so in the exchange, in the exact exchange, we have to sum over all of these occupied states in the like in the formula of the exchange exchange integral. And then after we sum over all of these states, all of these phases will cancel out. Like it will like behave like interference, and then the Hamiltonian is still local in a sense. It doesn't go like 1/r, like the Coulomb interaction. So it will be, if we use like a hybrid functional, it will indeed be less local in the PB case, but still it's doable. Yeah.
Sure. I mean, there's various levels of locality, right?
Yes.
But fundamentally, I mean, there are going to be systems where there are non-local Hamiltonian elements, right? I mean, if you have long-range Coulomb interaction. I mean, all sort of like dispersion or something. I mean,
Yeah, but still these long range. So if you consider the Hamiltonian, so in most cases this long range interaction will be cancelled out, like because of these interference I have discussed in this. But still there are cases, yes, like off diagonal long range order. But these of course these systems cannot be handled by our framework. But these systems cannot be handled by DFT anyway.
so, right. I mean, if you just have an ion, right?
Yeah.
And that's gonna affect the Hamiltonian elements at long range, right?
But at most it's a dipole potential.
Yeah,
But yeah, so
but DFT can do that. So
yes, sure. So you're mentioning if we move an atom, it will cause long range potential and will affect the Hamiltonian like very far away.
yeah.
Yes, that might happen, but still that potential goes off like a dipole potential, and this dipole potential is proportional to the Born effective charge of the atom. So we have to be specifically careful with systems like ionic crystals, where these crystals have very large, these atoms have very large Born effective charges.
Right. I mean,
Yeah.
so in the materials, it saves you, but like for molecular systems, you're gonna have these long range interactions. I mean,
That's possible. Yes.
it's future work.
Yes, and also our work actually works better in solid state systems than molecules.
That makes sense.
Yeah.
Okay, let's thanks Xiaoxun and
Thank you. Thank you.